Hello everyone, welcome to another tutorial video on the physical oversampling in Python. Today we'll talk about how to merge two level 3 data objects along the axis of time. So before we dive into the technical details, after last week's video, I received a few questions about using the proper Python environment. So the best practice is to use Anaconda and create a dedicated environment for the physical oversampling in Python. So if you go to the GitHub repository at the same level of the main script, this poppy.py, there is another file called readme.yml. It's one YAML file that contains all the necessary packages. Well, not all the necessary packages, the essential packages, and feel free to add your own packages. And here is the instruction on how to create your environment with such a YAML file. So, and then I had a few additional steps to make the Python environment work for Jupyter Notebook. And of course, you can use your favorite Python environment. It could be IPython or Spider or something else. So as you can see here, we have the Jupyter Notebook from the previous tutorial. And I can create a new one for this week. So in my system, the conda environment is called poppy_geopandas. Okay, so this will be the notebook for this week. We'll call that tutorial 1. Okay, and I will just copy some existing code from last week. So this will load the necessary functions from the Poppy library and define the text file used to download ChopOmi level 2, ChopOmi L2 level 2 data. So we run this piece of code to download 1 day of ChopOmi data over the contiguous United States. But today we are going to work with 2 days of data. So we will oversample the ChopOmi data for each day, create an individual level 3 object, and then we will merge them together. So if we change this, the start and the end time from the beginning of September 1st to the beginning of September 3rd, then it will contain 2 full days. And if I run this cell, it will download the ChopOmi data for those 2 days. And I have already done that. So this is the path that we have specified to save the level 2 data right here. And we can see now it contains the data for both the 1st of September and the 2nd of September. Okay, and similarly, we will oversample the data for September 1st and then later for September the 2nd. But today, we are not going to use the entire contiguous United States domain. We will focus on the Northeast. So we will make the domain smaller. And since the domain is smaller, we can make the block size smaller for each core. And for this task, I will only use 28 cores. So if we run this, it will create the level 3 object for this spatial interval and this temporal interval. So I will call it level 3A. And similarly, I will create another level 3 data object for the second day, everything being the same, but only changing the start and ending time. So now while it's running, after we have that level 3 objects, we can merge them. Okay, so now you can see the first day is finished, and now it's working on the second day. Then we can create a merged object. We call that L3AB. So we can do that by merging the second day into the first day. So this level 3 AB will be the level 3 data averaged for both days. And of course, we can do another way. So we merge the first day into the second day. The result will be exactly the same. Now, I also want to take this video as an opportunity to introduce more functions in the plotting, in the visualization. So since now we have the level 3 data for the 2 days, as well as the one merging them together. So we will create a 2x2 panel of subplots. And to make maps, we want to use a projection. So let's import the CartoPy library. And I want to make sure the lowest and highest column number density in all the subplots are consistent. So the lowest tropospheric column of NO2 should be 0, and the max that's used 100 micromole per square meter. Then we will use we'll create a matrix of 2x2 subplots, and for each subplot, we use a projection. And we'll loop through all the subplots. So we want to plot the level 3 data for the 1st of September, the 2nd of September, and the merged one, and also the merged one, which should look exactly the same. So now in each iteration, we will just have a temporary level 3 object and plot it. We can specify the axis on which we want to make the plot. We are not going to draw the color bar for now. We will draw the color bar in the end. And specify the minimum and maximum. Okay, so that should give us something. Okay, so now you can see on the top left, that's the level 3 data for September the 1st. Apparently there was a frontal system with thick clouds. So the satellite the satellite data were missing for a large part in the Northeast. But on the second day, the weather system moved towards the ocean, and we had fair weather for most part of the domain. And the top row, the bottom row are the merged ones. Those are the same because it's equivalent to merge the second day to the first one versus merging the first one into the second one. So we can add a few more steps to make the plots publication ready. So first we can add the title for each subplot. So I want to highlight the beginning and the end of the time intervals for each subplot. So for here, I just want to show the month and the day. Then in the end, I want to add a color bar. So this figure out is a dictionary returned by this plotting function. It contains some useful information for each subplot. So this PC is the p-color mesh object, and we can use it to create a color bar. We can label this. So this is tropomi NO2 data. Tropospheric vertical column density. And the unit is micromole per square meter. Oh, that's why we still had a color bar. There was a typo. It should be Joe color bar. It didn't report an error. That's strange. Oh, another typo, color bar. Okay, so now you can see the top row is individual days, level 3 data. But if you only oversample one single day, then the level 3 data makes little difference. It will just look very similar to level 2 data. For example, this is level 2 data. It's defined on the native spatial and temporal resolution of the instrument. But level 3 data really become very powerful when you average over a different and very flexible range of spatial and temporal resolutions. So for example, in the bottom, we average over those 2 days. So now you can see the gaps are filled by different days. So for example, in the ocean, the data are missing on the second, but it was available on the first. So when you average those two, those gaps are filled. Okay, so that's it for this week's video. Thanks everyone for watching, and I hope to see you in the next tutorial video.